Hello, thanks for signing. Welcome to DefCamp, guys. A couple of words about myself before we start. I'm coming to electronics engineering, master's in cybersecurity, work in enterprise, problem management, and availability capacity management, with passion about cybersecurity. And moved to a company that does industrial control and automation, basically helping develop the IT architectures and communication, and then trying to cover the cybersecurity part. Before the next slide, just a show of hands, who's familiar with industrial control systems? Okay, if you guys won't mind, we'll go through a crash course in industrial control systems and the equipment that are involved to understand exactly why these threats manifest and what the actual problems are. A couple of words about the company I work with. We operate in 7 industries: power generation, transmission, distribution. Our expertise comes from this field, the energy sector, and automation systems and protection systems for the energy sector and to other automation areas. Engineering consulting, substation automation, and protection systems, which is really delicate. Process control, electrical automation, and as we developed the IT and telecom side, also we started developing the cybersecurity side. About industrial control systems and what is different about them. Just to have an idea, this is corporate IT or traditional enterprise infrastructures and automation, the current subject we're going to be talking about. First and most important, corporate IT usually is not life-threatening, but when it comes to industrial to automation systems, safety does come first. Keep in mind that availability is important in enterprise environments. However, in industrial control systems, you can't actually disrupt the system without completely stopping it, so availability is critical. You have different vendors, that would be an important one. And you have a lot of devices here, not as many people, which is, it's on the good side. You don't have a lot of people doing whatever they want with their systems. You generally have a network that does the control of the process per se, a lot of devices, and just the operating staff. And the networks are rather flat and simple and not a lot of complicated communication, which are a lot of good advantages. If in general we talk about PCs and servers in the enterprise environment, here we talk about sensors, controllers, and of course we do have some servers. Just a quick run through these. Another important subject would be the operating systems. Here you have a lot of vendor-embedded operating systems, which of course come with their own vulnerability. You have your vulnerabilities for Windows and Linux. These vendor-developed systems have some real issues. Just to move to the next slide, this is rather general. This is very important. Keep in mind that industrial controls infrastructure are developed with a 25-year lifespan. So you're not developing this to be used for the next 5 years to see a return on investment. You're developing these to be functional for 25 years. That's why you see a lot of legacy devices and legacy technology still present in most operating control infrastructures. And you have this technological freeze when you actually put into production a power plant or a system, and generally you just freeze it there. That was the general concept. We're not going to do any modifications to it, we're not going to touch it, it's just going to run the same way for 25 years. Of course, there are some variations. We still have upgrades, different implementations, integrations, and that's where you start bringing in new technology. And usually there's a serious gap between those two technologies. And as built is the documentation that shows you how an infrastructure should look, the architecture and the systems involved. The problem is you don't actually have them up to date, and a lot of process control operators don't actually know how their infrastructure is actually composed of and how it's working to the finest detail. They're more interested in just controlling the infrastructure and the system. The only time you can actually do changes to these systems is during shutdown periods. Being a control live infrastructure, you're going to shut down the whole system completely, and that's the interval where you can actually do any modifications or upgrades. We had the customer that has a shutdown window of 10 days per year, and all the modifications, all the vendors come in those 10 days per year and start doing all the upgrades and modifications. So it's another important aspect. Why do I say AEC and not CAA? In enterprise, you have confidentiality, integrity, and availability, and those are the key the order of your importance. In control systems, confidentiality is not that important. Don't care to protect the actual values of the variables of the process. You're very interested in the availability of the system, the integrity of the system, so the values aren't altered or the system isn't working outside of its normal parameters, because it can have a serious effect. And last, confidentiality. But this completely changes the paradigm of how you can secure these systems, because you're not looking at securing the data per se, you're looking at securing the process itself. Information technology and operational technology convergence. This is what I was talking about, the legacy technology, the old operational technology you have in your infrastructures, and the way they are converging with the modern IT. And this brings a lot of opportunities and challenges. An example, we all know information technology you have present in all enterprise systems, your server computers, firewalls, your general stuff. Operational technology have a couple of particular elements, and we're going to go through them a bit to understand the roles of each of them. HMI is a human-machine interface. Usually it's the system through which you control the entire process. You have a small diagram of the system and the most important commands or values you're interested in, and you're supervising the system and trying to control it from one single interface, a human-machine interface. It can be for a dispatch center, it can be locally for every subset of the process, but usually it's just an interface. Historian is just a database that stores all the values of the process. You use this having all the values, you can do the graphs, do analysis on the production environment. That's the data you use to actually analyze the environment. We'll go through these in the next couple of slides, control space and use, and understand exactly what their role is. These two have converged, bringing their advantages and, of course, a lot of challenges. The advantages of modern technology we all know, and they're really good in the industrial control systems. It's the standardized hardware and software, pretty much off the shelf. You have the interoperability, cost reduction, increased speed. We all know the advantages. The disadvantages is disruptive innovation, which you have in IT. You can actually bring that to operational technologies. Here, you need predictability and stability. It's the most important part. There are different mindsets. For the OT, you really need to run the process in the same way for a lot of years to come. There's a very strong knowledge gap. When I mean OT, just to clarify this, think of legacy technology like the serial communications. Before there was TCP/IP, the legacy technology. And the knowledge gap is quite significant. People that operate OT infrastructures are not very used to or familiar or accustomed to these new IT mindsets that are evolving, fast growing, keep updating their system and stuff like that. They have no idea about updating their system. Usually you don't conceive of modifying or changing a system that took 5 years to develop and implement and actually build a factory with the whole automation process. And then I have an idea, let's innovate this. They don't want that. They need to have the return on investment. And that takes years. So let's go a bit through the key elements. Let's start with the basics. You have sensor and command elements. Sensors are the things that you gather from the field, from the actual device. You need to have some voltage, some currents, some sort of values that show you the current state of the process. And with the commands elements, you can take action on that system. And imagine a motor that's controlling the van or the conveyor belt or anything that needs a signal to start doing an actual action. These are the primary basic elements with which we actually control the process. All these data, they go into a PLC. A PLC, think of it as it's an embedded device, basically. It runs the variations of Linux developed by the vendors. You have does this have any sort of, what that is? You have a CPU that runs the Linux and a real-time operating system, and by real-time I mean the clock time is really, really short, so it gives you the sensation of real time. It runs the control logic in itself. So given the inputs it has on the multiple sensors, multiple modules, it takes quick decisions, it goes through some loops, and it takes decisions of what commands to send on the outside. So read data from the field and execute the control logic. Most of the logic is here on the PLCs per se. Cybersecurity-wise, there's not a lot of things you can do except limit the data flows, monitor the network traffic, and of course disable new services. But they don't have too much functions, as their primary goal is to operate real-time and take real-time decisions on the data it has from the fields. This is one of the most critical parts of industrial control systems. All those PLCs send data to a remote telemetry unit via industrial communication protocols. So it has an intermediary data storage, it's a real-time database. It does the protocol translations, because PLCs or different zones of the infrastructure can talk on different protocols. And you need to unify those and take them to a unified language. This is where the RTU comes in. Usually you can talk on multiple industrial control protocols. Again, not very much cybersecurity you can do on them. Lately I've seen some firewalls embedded with just layer 4, I think. Yeah, layer 4. These are processor historians and computers. The human-machine interface I was talking to you about, that's an example of an HMI we included for client. They run on regular x86 computers. They have typical operating systems, and usually it's Windows, all variations of Windows, from Windows 32 to Windows 10 lately. Using off-the-shelf technology, so this is basically just brought in from the enterprise environment, and you're running an application on it that allows you to control and monitor this process. Of course, you have, again, your networking devices, which are typical with other enterprise solutions. You do have the switches. Particular things about them, they're industrial grade, so they are capable of sustaining high temperatures, electromagnetic fields, particularly done for industrial systems, but pretty much in general managed switch. Routers, again, same technology you would see in the enterprise, just that the hardware per se is designed to withstand extreme temperatures and conditions. Okay. Firewalls, you've seen them lately, similar thing. Just as a hint in the industrial area, you see a lot of layer 4 firewalls. Actually, we need some UTM on that, and just a general recommendation, so this is typical, you see it everywhere. Protocols. In the industrial control area, you don't see the general enterprise protocols. You see protocols dedicated to carrying data from the field, from the PLCs, and send them upstream. You have Modbus, one of the first industrial protocols developed by Modicon. It's serial NTCP. And it's a master-slave system, so we're still in the area of master-slave here. DNP3 is pretty much a US version of the EEC 104. Server-client approach, and EEC 61850 is primarily used in substation environments, and it has what we call goose messages. It's a message that you need to send from one substation to another in under 40 milliseconds for them to trip the circuit breakers, to decouple the substation in case of a fault on the line that's connecting them. Usually you have fiber optic implementation to transfer that, otherwise it's going to take a while. This is your typical architecture. Let's say you have your sensors here, they're all communicating to, all the data from the sensors is taken and sent to a PLC, which sends them upstream to the RT or to the control server. Your typical DCS architecture. Let's get to the juicy part. So taking that into context, the evolution of threat, and I'm going to start with something that you probably all heard of, but it's really important. Stuxnet. It's an overtalk subject. I'm not going to bore you too much with it. But keep in mind the years. So this happened in 2010, and with no direct access to the facilities or an isolated network, it took out 1,000 centrifuges. So this is according to the International Atomic Energy Agency. It's really funny that this was pretty much, given the context, this was the first cyber weapon we've seen. And it was used to target on isolated networks, and we keep having in industrial control systems the idea and the paradigm that if your network is isolated, you're safe. We had a customer, his network was isolated, and by that I mean military-grade guards at the entrance to the facility. No laptops, nothing except for contractors that actually needed to perform maintenance. And we wanted to take a file of the configuration and look at it afterwards, plug the USB stick in, and we got a whole collection of malware from that network, dating back from the past 10, 12 years. So it was a complete air gap to isolate networks. The viruses weren't getting out, that was for sure, but they keep getting in. This was interesting for Stuxnet that it modified and hides code on the PLC. So you had your PLC and you had your HMI, let's say, and you were sending commands from the HMI. It looked like the commands were going fine. The PLC said it received the proper commands, however, it did something completely different. That's why it was quite hard to detect in the first place. Just going to go to the next two slides. So Havex was pretty much the most sophisticated long-term cyber espionage campaign we know of. It lasted for 3 years. It targeted power grid, petrochemical asset owners, and even pharmaceutical owners. So leveraging OPC vulnerability of the industrial control protocols. OPC is very general used in an old industrial protocol. Without any physical destruction or actually targeting the system, the malware was present in the network and kept exfiltrating information. Recipes for the pharmaceutical industry, or any other configurations or data that would be valuable for further use or could be sold on the black market. And keep in mind the years. In 2014, we see the first use of an advanced persistent threat malware toolkit to develop modular malware targeting power generations. So this was 4 years after Stuxnet, and they're developing modular malware targeting power generations and large suppliers. A lot of systems in NATO, European Union, and the energy sector were affected. It's interesting because in the next slide, so 1 year afterwards, at the end of 2015, Ukraine is under attack, and we have 30 kV, 30 substations taken out. How was this performed? I was telling you have contractors that come and do maintenance on the systems, and perform upgrades, O&M in general. One of the contractors, to try to show his competences in different technologies and different equipment, was publishing on his website what equipments or what solutions he used to perform various upgrades to these substations. Basically giving you a lot of insight into what exactly devices they have in the network. Through the contractors, they managed to get access actually to the credentials of a user that had VPN access. The attack is really simple. So they VPN'd in, they took control of the HMI from the dispatch center, and they just moved the mouse, opened all the circuit breakers, taking out 710 kV substation and 35 kV, basically leaving without power 225,000 people. And not just home users, hospitals, any facility, industrial site, everything was blackout for 6 hours. They also did a denial of service on phones, basically calling them in so they couldn't call out. And also, they took out the serial communications to make sure that you can't access the systems through other locations that have management control of the place. And this whole beautiful setup, at the end, they completely wiped out the computers. So the entire automation solution went to shit. What was this supposed to do? They lost everything. So that's why it took 6 hours, because they had to do a fallback to the manual solutions and the legacy devices that they had in place at that point. The attack was rather simple. I mean, nothing very sophisticated took place, just some spear phishing, some long-term campaign for a couple of months, your basic stuff. But it was the first known instance where a cyber attack had disrupted the electrical power grids. This was 2 years ago. And this takes us to 2016, last year, December, Ukraine again. So probably this year it's going to be the 3rd edition. It's happening every year, it seems. But this time we see a collection of everything in the past summed up into something that's rather dangerous. We have a modular framework dedicated for industrial control systems nowadays. So this was named Crash Override. It targeted Ukraine again. This time, it wasn't that of a simple attack of taking control of an HMI. This time we had malware developed and dedicated that could talk on your general industrial control protocols, so 101, 104, 6185 for the substations, and OPCDE. So this malware is capable of communicating with all the industrial equipment in the network. Now we have a serious problem. We have the classic data wiper that wipes the drive screen. We have the ability to expand and add further industrial protocols to it. And rather important, it had an exploit for the Siemens cProtect 4. So cProtect 4, this is a protection relay. It's similar to, I don't have the names. It's takes currents, it reads currents from the system, and when it has a certain anomaly, it decouples the substations from the network to isolate it and protect it from further failures. In general, just to protect the transformers, which are really expensive and they're usually custom-made and take months to actually develop. Keep that in mind, transformers take a lot of time to build. It's not something you buy off the shelf, and it's not something you have in stock in the world in general. When you need one, you need to custom order one. This killed the equipment that was meant to protect the whole substation. It only lasted for an hour. which you'd say it's fine. But it attacked this time not the distribution substations, the one that send energy to the final consumers and to consumers in general, but the transmission substation. The transmission substations are the ones that link various regions in the country and do the ring of transporting the national energy. These are really critical and vital for the whole country. In the sense that if you take out enough of them, you can cause a general blackout. And again, with the problems and issues arising from trying to bring that up again. It only took out 200 megawatts of capacity. From my point of view, this was, I'm not sure if it was intentional, because one of the issues we have with general cyber weapons is once you use them, people are aware of the technology you have and the solutions you have to attack them, and they can either try to find some ways of actually protecting themselves, but for industrial control systems, having a lot of legacy technology is quite hard. But also, you have the issue that you just take out one substation from Kiev North, and you do an impact for an hour. The previous attack lasted 6 hours, took out 30 substations. This time you're just taking out one. Not sure if this was a proof of concept or it was an accidental use of the code, but for sure in just 6 years we have a dedicated malware capable of attacking any industrial control infrastructure. Within control infrastructures are still legacy and don't have the solutions to protect themselves, and you can't actually perform upgrades just like that. You need to change the whole process, you need to contract someone, design the whole system again. So it takes a couple of years and a lot of money. Not a lot of solutions for this except to actually monitor your network and try to see if you have any insights for it, any details that show any abnormalities or something that's trying to use the vulnerability of the OPCDA to scan your network. But if this hits you and you have a substation, not a lot you can actually do. Appears more proof of concept, blackout for about an hour. So these are the 5 main cases that I wanted to show you guys to understand how fast the threat evolved to industrial control systems, and not industrial control systems in general, but especially for the energy sector, which we think is rather vital. And given the short lifetime and the complexity of the system, this is a real challenge nowadays. Just so to have an idea where we are now and what to do next. Weaknesses, gaps, and vulnerabilities. You're familiar with this, and they're present in the enterprise environment, but in the control environment, they're everywhere. You don't have awareness or training among employees whatsoever. You have little proper network segmentation. You have some IT firewalls, and you see this attempt to try to modernize your network, and you bring IT firewalls. They don't help you a lot, because you need OT firewalls in the sense that they need to understand the industrial protocols and try to actually read the values and variables that are being transmitted through that network and try to protect you with some deep packet inspection. The boundary between the IT, the enterprise environment, and the OT environment is rather thin. A lot of connections and a lot of attempt. You have connections to the enterprise environment because you need to do the billing, you need to look at various data from the process. In general, you need access to have that infrastructure produced for you and understand exactly what is producing, monitoring, and operating. Default accounts, like everything, there's a lot of default passwords on most of the equipment, and legacy and unpatched systems. The level of unpatched, keep in mind we have Windows XP still in a lot of systems. They're not going anywhere anytime anytime soon. It's impossible to upgrade and modernize all these systems in the next 10 years. It's just we don't have the manpower to actually do that. Even if we wanted to, and we had really low cost, we don't have the manpower for it. Legacy and on-base systems, lack of visibility. This is again a real problem. This is just going through the steps that would be needed to actually secure your infrastructure nowadays and to have an idea of why this is quite complicated. You need to first update the as-builds. To update the as-builds, you need to go into the facility, take every wire, and see where it starts, where it ends, and rebuild the whole network topology of the infrastructure. Man-hour and the labor work is quite intense on this, just to have a picture of what the infrastructure looks nowadays, after all the contractors, after all the upgrades, after different maintenance and modifications to the solutions. We had some PLCs broken, someone changed them. They didn't have the same equipment because it's not being manufactured anymore. The initial one was built 10 years ago. So, of course, you have a lot of variations. Just updating the as-built takes a lot of time, a lot of work. Then, assuming you would actually have the proper capability and try to integrate it into a dedicated SOC, there are not a lot of security operations centers that are dedicated for control systems. They don't understand the technology or the way that the particularities of those systems. So it's quite hard to find any. And of course, training is, let's say, not the easy part, but it's something that we all know. Vulnerability management, that's okay, but penetration testing, again, is something that you can't actually do on a live system or on any control network. Being very old, if you run an Nmap on these systems, you might crash the PLCs, or some of the PLCs. They're that vulnerable. If you send them a TCP packet that's malformed, again, they might just crash and stop running. I had experiences with this. So you'd have to do the penetration testing on a separate environment that would be cloned, but it's hard to clone an environment at that scale. And take bits of it and try to just do pen testing on devices in an isolated environment. Unfortunately, a lot of the operators don't actually have the separate network, they don't have the devices for spare, they don't have an infrastructure on which you could actually do and start performing penetration testing. Improvement proposals, again, these are just your typical solutions, but it's to get an idea of the amount of work we're starting to do this, given the threat we're facing nowadays on critical infrastructures and critical to the energy sector also. In our vision, and this again is something that's security is the mindset and not the general solution. Why I'm putting this here is there is still this impression, I know it's present in the enterprise environment, but it's very, very present still in the IT environment, in the OT environment, that you're just gonna get someone with cybersecurity skills and they're gonna fix your network just like this. I've seen it. But physical, they have it covered. Usually in OT infrastructures, they're isolated, you can't actually access them. The architectures, we've seen lately a lot of architectures that do touch base on the subject of cybersecurity and propose firewalls, network segmentation, so the basics are starting to be there. No actual requirements on the hardware or software yet. Insight into the operations and actually see what traffic is going on through the network is not present. On most bits, we've seen no one's actually requesting you to look into the network and have a report from it. An operational procedure, of course, it's the same. Which brings me to education. And I'm putting this up there because we have a lot of infrastructures right now that will need security in the near future. We'll need upgrades and implementations to bring them to this year with the solutions. The ranking countries are the ones that have some of the most courses disciplines studying information security in general. In Romania, we only have for now just 4 courses. From what I'm aware, this is from ENISA, so I'm not guaranteeing on the accuracy. It's a role-playing system. So, just wanted to point out that we have a lack of workforce and people capable of understanding cybersecurity in general in the enterprise area. In the industrial control systems and in this field, there is even less skilled workforce, just because it's not just the enterprise IT you need to think of. You need to actually understand the control process and what is going on in that particular network. You need to have some understanding of embedded devices. You need to have an understanding of industrial control protocols. So they're not complicated skill sets, but something a bit different that you need to bring it all together. And education is important, and it's something we need to start focusing on in the future, because otherwise I don't see how exactly we're going to secure those devices that in 6 years had such a fast-growing threat to them. And all modern upgrades or any other implementations, they rely on modern technology. So the exposures of these devices keeps getting bigger and bigger by the day.